Welcome to Sleepy Stories. In this episode, we will take a clear and steady look at space and stillness so that you can learn about the quiet side of the universe while you rest. If you notice that you do not fall asleep immediately, that is completely fine, because your mind can still follow the simple explanations and collect a few interesting scientific facts before sleep arrives in its own time. Simply listen, let your breathing slow, and allow the information to settle at its own pace. If you find these calm journeys through science helpful, you are welcome to support more of them by liking this video and subscribing so that you can return to them whenever you wish. Right now, there is nothing you have to do. It is enough to lie where you are. Feel the weight of your body supported, and let the night surround you while we turn our attention gently outward, beyond the air above your head, toward the quiet region where space begins. You can start by imagining the room around you with its familiar sounds. There might be a faint noise from the street or the distant hum of a device somewhere in the house. These sounds reach you through the air, which is full of molecules that constantly collide, bounce, and carry small pressure changes from one place to another. Sound is the pattern formed by those pressure changes as they move through the gas, like ripples on the surface of a pond after a stone has been dropped in. Now picture yourself rising slowly through that air, as if you were being carried upward by a gentle elevator that makes no sound at all. The ceiling falls away, then the roof, then the rest of the building, and the city below grows smaller while you continue upward through layers of atmosphere. As you climb, the air becomes thinner. There are fewer molecules in each volume, fewer collisions, fewer chances for a vibration to be handed along. The familiar sounds of streets and voices fade, replaced by quieter and quieter background noise. Continue this slow ascent in your imagination until you reach a height where the last wisps of the atmosphere trail away into near emptiness. There are still some atoms and molecules here, but far fewer than at the surface, and they are spread over a much larger region. A shout, a song, or a heartbeat would not travel far in such a sparse medium, because there are not enough particles close together to carry the rhythm of the vibration. In practical terms, sound loses its reach and then disappears, leaving no pressure waves to move information across the space. From this height above Earth, space opens around you as a dark, almost featureless background. Yet this darkness is not a sign of complete emptiness. Light from the sun streams past, some of it reflected from the bright face of Earth, some of it moving on toward other planets. High-energy particles pass by at great speed without making any noise at all. What you are imagining is a region that is silent to the ears, but still full of activity that moves in ways our hearing cannot detect. While you stay comfortably in your bed, you can let this contrast settle in your thoughts. The place where you are is filled with air and with soft mechanical noises, all carried by countless collisions of molecules. Just a few hundred kilometers above, the same planet is wrapped in a zone where those collisions become rare, where physical processes continue almost unnoticed and without sound. Thinking about this gradual transition from noisy air to quiet space can help your attention soften as you follow the path from the surface to the edge of the atmosphere. In your mind, you are still resting just above the upper edge of the atmosphere, where sound no longer travels in any familiar way. From this quiet vantage point, it might be tempting to think of everything around you as pure emptiness, a kind of perfect nothing that separates worlds. In everyday language, people often use the word vacuum to mean exactly that, a total absence of matter. In physics, however, the picture is gentler and more precise. A vacuum is not a place where absolutely nothing exists. It is a place where there is very little, a space where particles are so sparse that their encounters become rare events rather than constant collisions. Imagine a small room filled with air at the surface of Earth, and picture the molecules being removed from it one by one. At first, the pressure drops, the sound becomes softer, and breathing would become difficult. As more molecules disappear, sound fades because there are fewer particles left to pass the vibration on. If you continued the process, you would eventually reach a point where only a few stray atoms move through the room, perhaps a handful in the entire space at any given moment. That room would qualify as a very good vacuum by laboratory standards, even though it is not perfectly empty. Now stretch that room in your imagination to the size of a house, a city, a country. keeping the same few atoms inside. You approach the kind of scarcity that characterizes the space between the thin upper atmosphere and the regions where satellites travel. In low Earth orbit, and higher above, there are still atoms and ions drifting around. They are simply spread out over such large distances that a single cubic centimeter might contain only a few of them. Individual particles move, collide from time to time, and respond to electric and magnetic fields, but the frequency of those encounters is low. For most practical purposes, it is as if there is nothing there to push against. That is why spacecraft can glide so freely for long periods, needing only occasional corrections to maintain their tracks. Besides particles, space is filled with fields. The gravitational field of Earth extends far beyond its surface, guiding orbits and shaping trajectories. The magnetic field surrounds the planet, forming a shield that deflects many charged particles from the Sun. On top of this, there are electric and magnetic fields carried by light and by other forms of electromagnetic radiation. These fields are not made of solid material, yet they are real structures in space, capable of storing and transporting energy across vast distances. You can think of the vacuum not as a blank canvas, but as a very thin medium threaded by these invisible influences. A photon of light leaving the surface of the Sun does not require a road or a stream of matter to move along. It travels as a self-sustaining disturbance in the electromagnetic field, preserving its speed while the space around it remains almost entirely empty of particles. When it finally reaches an eye, a camera sensor, or a telescope mirror, it can deposit its energy and reveal where it came from. Even in the deeper regions between planets, tiny grains of dust float, tracing their paths under the pull of gravity and the faint pressure of starlight and sunlight. These grains are few, but over time they can gather into streaks and clouds, forming material for future structures. When you imagine the darkness between worlds, you can let this more nuanced picture take shape in your thoughts. The vacuum is quiet, sparse, and gentle, yet it is not absolute nothingness. It is a calm background in which light, fields, and occasional particles continue to move in ways that remain consistent and understandable. In the quiet picture you are building, one detail is especially important. The silence of space is not a mysterious property of the universe, it is the natural result of how sound works. Sound is not a thing that exists on its own. It is a pattern of motion shared by many particles together. When you hear a voice, the air near the speaker is pushed and pulled in small, rapid changes of pressure. Each molecule nudges the next one, and that one nudges another, so that the pattern of compression and rarefaction travels outward like ripples in water. On Earth, this happens easily because the air is dense enough for molecules to be very close together. When a vibration begins, there is always another particle nearby to take the push and pass it on. The pattern can travel through the air, through water, and through solid materials. Your bones, your skull, the walls of your room, and even the ground beneath the building can carry vibrations from one place to another. That is why a loud sound can be heard far away and why you sometimes feel deep noises through your body as much as you hear them through your ears. Now imagine trying to send that same pattern into a region where the particles are almost absent. At first, as the air becomes thinner, the sound grows faint. The wave still exists, but it loses strength quickly because there are fewer particles to keep it organized. Eventually, when the spacing between particles is large enough, the wave can no longer continue in a recognizable form. Particles may still jostle each other occasionally, but the motion is no longer a smooth, coherent pressure pattern. The concept of a sound wave stops being useful. This is what happens as you rise through the upper atmosphere and cross into true space. An engine that would roar on the surface produces no spreading wave in the vacuum around it. A bell that would ring clearly in a room becomes silent if struck in an airless chamber. The metal still vibrates, but with no medium to transmit that vibration away. The motion remains confined to the bell itself. Only if the vibration reaches your body through a solid connection, such as your hand on the bell, would you sense it. Astronauts experience this directly. Outside their spacecraft, in the open vacuum, there is no surrounding air to carry the sound of tools, footsteps on a surface, or the movement of equipment. When they work on the exterior of a station or a ship, they hear their own breathing and the hum of systems inside the suit, because there is air within and solid material all around them. If they tap a handrail that is attached to the structure, they may feel the vibration through their gloves and hear it as sound transmitted through the metal into the air inside the suit. But the space outside remains silent, no matter how much motion takes place there. Even dramatic events in space do not produce sound in the way they are often portrayed in films. A burst of gas from a rocket nozzle, an impact of debris on a metal panel, or the destruction of a fragment of equipment all involve forces and changes of motion. They may send shock waves through the material of the spacecraft, and those waves can be heard by anyone inside. Yet the surrounding vacuum carries only particles and radiation, never pressure waves of sound. Light, on the other hand, has no such limitation. It is not a vibration of matter, but a changing configuration of electric and magnetic fields that sustains itself as it moves. A star that flares, a planet that reflects sunlight, and a distant galaxy all send information outward this way. The vacuum that refuses to carry sound allows light to travel almost unhindered over enormous distances. As you lie where you are, you can hold this distinction in mind. The air close to you is busy and full, capable of transmitting the softest whisper or the faintest creak. A short distance above, the air thins, and sound begins to lose its strength. Higher still, sound falls completely silent, and only light and a few scattered particles remain to cross the space between worlds. Light, unlike sound, does not depend on a crowd of particles to move. It travels through space as a self-sustained pattern in the electromagnetic field, a relationship between electric and magnetic components that keeps renewing itself step by step as it moves forward. If you imagine a single disturbance beginning near the surface of a star, you can picture it as a small variation in that field, changing in time in such a way that it creates the next variation, and the next, and the next, even when there are almost no particles around to be pushed or pulled. When you look at a star in the night sky, you are seeing light that has crossed vast distances of near vacuum without needing air, water, or any solid structure to carry it. Each tiny packet of this light left the star long ago, traveled on its own through the emptiness, and finally encountered your eye. The space it crossed can be almost completely empty of atoms, yet the path is still there for the photon to follow. The silence that prevents sound from spreading is not an obstacle to light. It is more like a clean, clear path where light can move freely. Physicists describe light as part of a wide family of electromagnetic waves. The visible colors that your eyes can detect are only one narrow band. At longer wavelengths, there are radio waves and microwaves. At shorter wavelengths, there is ultraviolet, X-ray, and gamma radiation. All of these share the same basic nature. They are patterns in the electromagnetic field that move through space at a constant speed, carrying energy and information from one place to another. What changes from one type to another is not the basic character of the disturbance, but its scale, how many peaks and troughs pass by each second, and how tightly they are spaced. Because light does not require matter to travel, it can cross regions that are almost empty and still deliver detailed information about its source. When a star is hot, it emits a particular mixture of wavelengths. When it has certain elements in its atmosphere, those elements leave precise signatures in the spectrum of the light. A planet that reflects starlight modifies that light in specific ways, depending on its surface and clouds. By capturing these faint signals with telescopes and detectors, scientists can reconstruct what is happening in places that no spacecraft could reach in a human lifetime. You can think of the universe then as filled with quiet, invisible ripples of light moving in every direction. Some come from nearby sources, like the sun and the planets. Others began their journey in distant galaxies, long ago in the history of the cosmos. They crossed the silence of interplanetary and interstellar space without needing to disturb any medium. When they finally interact with matter, they can warm a surface, trigger a chemical reaction in a cell, or release electrons in a sensor that records their arrival. Even in the space close to Earth, where satellites and stations move along their orbits, this ocean of electromagnetic waves is present. The sun sends a broad spectrum of radiation. The planet itself shines in infrared, releasing the energy it absorbs during the day. Human technology adds its own signals, from radio transmissions to radar pulses, all layered on top of the natural background. Much of this is too weak for human senses, but instruments pick it up and translate it into forms we can see and understand. If you return in your thoughts to that quiet point just above the atmosphere, where sound no longer spreads, you can picture yourself surrounded by these invisible messages. They do not press on your skin or stir the air, but they are there, flowing past in all directions. Some come from above, some from below as Earth reflects and emits, some from the sides as distant sources send their light on crossing paths. It is a gentle crossing of signals, a calm traffic that continues day and night without any noise. This contrast between silence and unseen communication can be a steady idea to rest on. Around you in your room, small sounds move through the air in the familiar way. Above, in the vacuum, pressure waves fail and sound falls away, yet information still travels quietly as light. The same underlying rules apply everywhere. Where there is matter, sound may form. Where there is emptiness, light still moves. Both are part of a single physical description of the world, each active when conditions allow. As you lie there, you do not need to hold on to all the details. It is enough to keep a simple picture. Close above the air, there is a region where nothing can carry a shout or a whisper, yet light from stars, planets, and galaxies passes through without effort. In that region, the universe shares its state through silent signals, and those signals eventually reach instruments and eyes on Earth. The silence of space, rather than being a blank, is a background that lets these messages cross without disturbance, joining your quiet thoughts as they drift and slow. Imagine now that instead of hovering just beyond the atmosphere, you are riding inside a small spacecraft circling Earth. Outside the window, the planet fills much of your view, a curved surface of land, ocean, and cloud sliding beneath you. Inside, objects do not sit firmly on tables. They drift. A loose pen floats near your hand, a droplet of water hangs in the air, and your body no longer feels pressed into a mattress or a chair. The sensation is not of rushing but of suspension, as if the usual downward pull has quietly stepped aside. This feeling comes from a state known as free fall. The spacecraft and everything in it, including you, are constantly falling toward Earth under the pull of gravity. At the same time, the craft has a sideways motion fast enough that as it falls, the surface of Earth curves away beneath it. Instead of plunging straight down, the vehicle follows a continuous arc around the planet, and the path closes on itself as an orbit. Gravity supplies the inward pull, while the sideways speed keeps the craft from ever reaching the ground. Because everything around you shares this free fall, there is no supportive force from below like the one you feel when you stand on the ground. On Earth, your weight comes from the floor, pushing upward on your feet while gravity pulls you downward. In orbit, the structure of the spacecraft falls with you, so it does not need to push hard in any direction. Your body and the cabin follow the same curved path together. The result feels like the absence of weight, though gravity is still present and only slightly weaker than at the surface. In this environment, motion behaves differently from what you are used to in daily life. Give an object a small push, and it will continue drifting at nearly the same speed and in the same direction, because there is very little to slow it down. To stop yourself when you start moving, you need to grab a handhold or touch a wall. Small actions produce slow, graceful changes rather than abrupt stops and starts. Movements that would be routine on Earth, like turning a wrench or pushing off from a surface, become deliberate and measured to avoid unwanted spinning. From the point of view of someone inside the spacecraft, this can feel remarkably calm. The background forces that normally press on muscles and joints are gone. When onboard systems are quiet, the cabin can feel almost like a still pond in which you and the objects around you float. Yet if you could look at the scene from far away, you would see the craft tracing its path high above the planet, circling again and again in a steady rhythm. This contrast between external speed and internal stillness is an important part of how motion works in space. The laws of physics do not require that movement always feels dramatic. When changes in speed and direction are gradual and shared by everything in the same frame of reference, the experience can be one of deep quiet. Inside the spacecraft, you feel only the gentle effects of the motions you choose to make. As you rest where you are now, you can borrow this image. Your body is not orbiting the planet at high speed. yet it is carried by Earth on its steady path around the Sun. There is constant motion in the wider system, but at your scale it feels like stillness. The bed supports you, the room encloses you, and the larger motions of Earth and space unfold without needing your attention. You can let your thoughts float for a while, like objects in a cabin in orbit, drifting slowly until they come to rest wherever they naturally settle. If you bring your attention back to your own body for a moment, you can notice that you are already living inside a quiet balance of forces. Gravity pulls you gently downward toward the center of Earth. The mattress, or surface beneath you, pushes upward with equal strength. Your muscles do not have to fight these forces constantly, because the structure you lie on carries most of the load. When the downward pull and the upward support match, your position does not change. You remain where you are, not because nothing is acting on you, but because the actions cancel. This kind of balance is what physicists call equilibrium, and it appears in many places in the universe wherever apparent stillness is found. You can picture a simple object resting on a table, perhaps a book or a stone. Gravity pulls it toward the ground, the table pushes back, and the forces meet in the middle. The object feels quiet, but within it, atoms still vibrate. Electrons still move, and fields still permeate the material. The stillness you see from the outside comes from the way the larger influences oppose one another. If the table were suddenly removed, the balance would break and the object would begin to move. As long as the support remains, the alignment of forces holds its shape and the object stays in place. In space there are similar balances, even when there is no solid surface to rest on. An orbit is one example. A spacecraft circling Earth is pulled inward by gravity, while its sideways motion tries to carry it in a straight line. The result is a curved path that wraps around the planet. At every point on that path, the inward pull and the tendency to move forward combine to produce a smooth, unending fall. From far away you could describe this as a constant change of direction. From inside the craft, where everything shares the same motion, it feels like weightless stillness. The equilibrium here is not between gravity and a supporting surface, but between gravity and motion itself. There are other, more delicate forms of balance in the gravitational field around Earth and the Sun. In certain regions, the pulls of these two bodies combine in such a way that a smaller object can maintain a nearly fixed position relative to both. The exact details are described by mathematics, but the underlying idea is simple. Where forces and motions line up just right, an object does not need large corrections to remain in place. It is not truly motionless. It travels along with the larger system, yet it does so in a way that preserves its relative position. From the perspective of the object, the environment can feel remarkably stable over long periods. Inside your own body, similar patterns appear. Muscles that would have to work constantly if you tried to hold yourself rigid in mid-air can relax when a surface takes their weight. Joints settle into angles where ligaments and tendons are not stretched to their limits. Even at the level of cells, pressures and concentrations adjust so that fluids and dissolved substances reach balances across membranes. None of this means that nothing happens. Instead, it means that what happens is arranged so that opposing tendencies meet and neutralize each other. Where this occurs, tension drops and motion slows. As you lie there, you do not need to force yourself into stillness. You are already supported by a network of balances. Gravity, the strength of the bed, the shape of your body, and the quiet work of countless small processes cooperate to keep you at rest. Thoughts may still move, but they can move within a framework that does not demand rapid action. If sleep has not come yet, that is completely acceptable. Your role is simply to allow these natural equilibria to take shape, to let muscles soften where they can, and to notice that much of what keeps you in place is automatic. In the same way that orbits, surfaces, and gravitational balances hold objects gently in their positions, the structures around you and within you are already doing most of the work of keeping you safe and still. You can now let your imagination sink back down through the atmosphere until you are once again aware of the surface of Earth, but this time with a clearer sense of how much motion lies hidden beneath your everyday rest. While you lie still, the planet carries you along a curved path around the Sun. The ground feels firm and unmoving, yet the whole world is in continuous flight, tracing its orbit without pause and without needing to be steered by any hand. The speed of this motion is large when expressed in ordinary units. In the time it takes to read a few pages or to drift towards sleep, Earth has already traveled a significant distance along its path. Despite this, you feel no rush of wind, no sideways pull, and no sign that the scenery of the sky is sliding past. The stars appear steady from night to night, and the sun rises and sets with reliable timing. Nothing in your direct experience announces that you are part of a high-speed journey. The reason for this quiet lies in how motion is detected by your body. What you directly feel are changes in speed and direction, the accelerations that press you back into a seat or pull you to one side in a turn. When motion is smooth and nearly constant, with no sudden shifts, your senses register very little. On Earth's orbit, there are changes in direction all the time, because the planet follows a curve rather than a straight line, but these changes are very gentle on human scales. Gravity supplies the inward pull, and it acts equally on everything nearby, so there is no sharp difference for you to feel. You may have noticed a similar effect in daily life. When a train moves at a constant speed along a straight track, you can stand, read, or rest without being strongly aware of the motion. Only when the train starts, stops, or turns do you feel the pull on your body. In orbit around the Sun, Earth behaves like a train that has been running smoothly for a very long time, following a track that bends gradually but never produces abrupt jolts. The entire environment you live in moves with it, so there is no fixed point that would make the motion obvious to your senses. Over longer periods, the details of the orbit change slightly. The path is not a perfect circle but a gently stretched ellipse, and the speed varies a little as Earth comes closer to the Sun and then moves farther away again. There are also small influences from other planets, which tug on the orbit and shift it by tiny amounts. Astronomers can measure these variations with careful instruments, but in daily life they pass unnoticed. The overall pattern remains stable enough that seasons repeat and the sky returns to familiar configurations year after year. As you think about this, you might picture Earth's orbit as a wide track drawn in space, with the planet gliding along again and again. The track is not a physical rail, yet the path is defined by the same rules everywhere, so the motion repeats within narrow limits. Your resting body is a small part of this larger movement, carried along without effort or awareness. There is no need for you to do anything to maintain the orbit or to correct the curve. You are simply a passenger on a world that moves smoothly through space, and the quiet you feel in your room fits naturally within that larger, gentle motion that holds from year to year. You can widen your view now from the single orbit of Earth to the broader arrangement of the solar system. Instead of imagining just one planet on its path around the Sun, picture several tracks at once, each one slightly inclined and slightly stretched, each carrying its own world along a fixed, repeating route. Mercury travels close in, Venus follows a little farther out, Earth and Mars circle beyond, and the giant planets sweep along even larger loops. From above, these paths form a set of nested curves, like slowly turning rings drawn in the dark. Every planet moves, yet the overall pattern remains stable for long periods, shaped by the same gravitational rules that keep Earth on its course. Within these planetary paths, there are smaller motions layered on top. Moons orbit their planets, tracing miniature curves around the larger tracks. You can picture the moon circling Earth while both move around the Sun, creating a looping path that never quite repeats in exactly the same way, but stays within familiar bounds. Other planets have systems of moons of their own, some tiny and irregular, some large enough to resemble small worlds in their own right. These satellites follow their orbits under the pull of their parent planet, while sharing the planet's journey around the Sun. From a distance, the details blur into a simple picture, each planet as a node in motion, accompanied by a retinue of smaller companions. Beyond planets and moons, there are belts and swarms of smaller bodies. Between Mars and Jupiter, many asteroids circle the Sun on varied paths, some almost circular, others more stretched. Farther out, beyond Neptune, there are icy objects, dwarf planets, and scattered fragments following elongated or tilted orbits. Comets come from even more distant reservoirs, spending most of their time far from the sun, then swinging inward along long, narrow tracks that bring them briefly into the inner solar system before they retreat again. Each of these objects responds to the same gravitational pull, adjusting its path as it interacts with the larger bodies but staying within a general pattern that can be traced and predicted. If you zoom out far enough in your imagination, the complexity of all these individual motions blends into something more like a quiet mechanism. The inner planets move more quickly than the outer ones, completing their circuits in shorter intervals. The giants move slowly, taking many Earth years to finish a single loop. Moons circle their planets many times during one planetary year. Asteroids and comets follow their own schedules. At any given moment, the positions of all these bodies differ from what they were a short time before. Yet the structure of the system remains recognizable. Planets do not suddenly jump from one orbit to another. Moons do not wander far from their parents. The arrangement has a layered order, like gears turning within gears at different speeds, all driven ultimately by gravity. In the background of this ordered motion, there are small disturbances. Planets pull on each other, slightly shifting each other's paths over long intervals. Asteroids can experience close encounters that alter their orbits a little. Comets lose material when they approach the sun, changing their mass and their future trajectories by small degrees. These effects accumulate, and over very long times the system evolves. However, much of this change is slow on human scales. For many generations, the apparent pattern of the solar system stays nearly the same, with the same major planets occupying the same general regions of space. This persistence is what allows astronomers to calculate positions far in advance and to design missions that navigate through the system using its regularities. As you rest, you can let this image of layered motion settle in your thoughts. There is constant activity at many scales, from the orbit of your own planet to the paths of distant icy bodies at the edges of the system. Yet when viewed from far enough away, the solar system appears as a coherent structure, not as a random swarm. Each object follows a route that fits into the overall pattern, shaped by a small set of shared rules. In the same way, many processes in and around you continue while you lie still, from the circulation of blood to the movement of air in your lungs and the slow drift of thoughts in your mind. When you zoom out from individual pulses and breaths, what remains is a sense of continuity, an underlying order that does not demand effort from you to maintain it. You are part of a system that keeps moving smoothly, even while you are free to be still within it. When you look at all the paths traced through the solar system, from the close inner orbits to the slow tracks of distant giants, a single influence runs through every pattern. That influence is gravity. It is quiet, constant, and always attractive, drawing masses toward one another without sparks, sound, or visible threads. There are no ropes holding planets in place, no hidden machinery pushing moons around their worlds. Instead, gravity acts at a distance, shaping motion in a way that is both simple in principle and rich in its consequences. The basic rule can be stated plainly. Every object with mass pulls on every other object with mass, with a strength that depends on how much mass is involved and how far apart the objects are. The closer two bodies are, the stronger the pull between them. The more massive they are, the more force they exert. In a system like the solar system, the sun's mass dominates, so its gravity provides the primary pull that guides planetary orbits. Planets also pull on each other, but their masses are much smaller, so their influence appears as gentle corrections rather than as the main effect. You can think of gravity as setting the stage on which motion unfolds. If there were no gravitational pull from the sun, planets would not curve around it. They would travel in straight lines, drifting away into the larger galaxy. With gravity present, any initial motion is bent into a path that curves, sometimes into a closed loop. When the speed and direction of a body match the pull of gravity in just the right way, an orbit forms. The result is not a static arrangement, but a dynamic balance, where continuous falling is matched by continuous forward motion. This organizing role of gravity is not limited to the solar system. On smaller scales, it helps hold moons in their orbits and pulls material into the shapes of planets and stars. On larger scales, it gathers stars into galaxies and galaxies into clusters, In each case, the same underlying law operates, differing only in the masses involved and the distances between them. Gas clouds collapse under their own gravity to form new stars. Loose swarms of material settle into disks and rings. Over time, loosely bound structures tighten and unstable configurations are smoothed out. The process is often slow. A cloud of gas and dust does not instantly fall into a star. It cools, fragments, and contracts over long periods. Parts of it may spin up and flatten into a disk. Collisions between particles within that disk gradually dissipate irregular motions, leaving a more ordered rotation. In this way, gravity, combined with the exchange of energy and momentum, tends to transform chaotic starting conditions into more regular arrangements. The paths of planets and the shapes of galaxies are outcomes of this patient, persistent shaping. Even when gravity produces dramatic events, such as the merging of two stars or the collision of galaxies, it does so by following the same set of rules. Two massive objects that draw each other together will accelerate, interact, and eventually combine or pass by, but the details of their encounter are still governed by the same equation that describes a falling stone. There is no separate set of laws for calm and for upheaval. One framework applies to both, and over very long times the tendency is toward bound structures that can survive for extended periods. On Earth, gravity feels like a downward pull, something that must be resisted by muscles and structures. In space, it reveals its broader character as the architect of motion. It curves trajectories, defines stable regions, and sets the conditions under which orbits and systems can form. Where other forces fade with distance or cancel out, gravity continues to act, guiding the large-scale distribution of matter. Seen in this light, the ordered motions of planets, moons, and smaller bodies are not coincidental. They are expressions of the way gravity quietly organizes matter into paths that repeat within narrow bounds. There is constant movement, but the movement follows lines that gravity itself has drawn in the possibilities of space. In the combined gravitational field of Earth and the Sun, certain special locations appear where motion takes on a particularly simple form. These are known as Lagrange points, named after the mathematician who first analyzed them in detail. They are not physical objects, but positions in space where the pull of gravity from the two large bodies, together with the motion needed to stay in orbit, can balance in a useful way for a much smaller object such as a spacecraft. To picture this, imagine the Sun and Earth as two masses in orbit around their common center, with Earth following its yearly path. Now consider a much lighter object, perhaps a space observatory, whose mass is too small to significantly affect the motion of the larger bodies. The observatory feels the gravitational pull of both the Sun and Earth. At most points in space, these pulls do not combine in a way that allows the observatory to remain in a fixed position relative to both. It either spirals closer to one body, drifts away, or follows its own orbit that gradually changes its alignment. However, there are 5 regions where the situation is different. At these Lagrange points, the combination of gravitational forces and the orbital motion of the system align so that a small object can maintain a relatively stable configuration. 3 of these points lie along the line connecting Sun and Earth, one between them, one beyond Earth on the far side, and one on the far side of the Sun. The other 2 form equilateral triangles with the Sun and Earth, one leading Earth in its orbit and one trailing behind. In a frame of reference that rotates with Earth around the Sun, these points appear stationary. The balance achieved at these locations is subtle. The object is not simply held in place by equal pulls, as a book rests on a table. Instead, the gravitational forces and the centrifugal effect associated with the orbital motion work together. At just the right distances, the inward and outward tendencies match in such a way that the object can keep pace with Earth as it moves around the Sun. The mathematics that describes this is precise, but the concept can be understood as a 3-way compromise between the Sun's pull, Earth's pull, and the tendency of a moving object to continue on its path. In practice, some of these points are more stable than others. The 2 that form triangles with Sun and Earth tend to be regions where an object can remain with relatively small adjustments. The ones that lie directly along the line between Sun and Earth require more careful control because small deviations can grow with time. Spacecraft placed near these points often follow small looping paths around them, known as halo or lysogous orbits, rather than sitting exactly on the mathematical point. Even so, the fuel needed to maintain these orbits is much less than would be required to hold a spacecraft in a similar position in open space without the benefit of this underlying balance. Because of these properties, Lagrange points have become valuable locations for observatories. A telescope placed near the point beyond Earth, on the side away from the Sun, can keep Earth and the Sun in roughly the same direction, making it easier to shield the instruments from direct sunlight and thermal changes. At the same time, the telescope has a clear view of the wider universe without Earth frequently blocking its line of sight. Other missions use different points for their own advantages, such as constant viewing geometry or stable communication lines. If you imagine the orbital paths of Earth and a small observatory together, these regions can be visualized as gentle hollows in an otherwise sloping landscape of possible motions. A spacecraft that reaches one of these hollows can spend a long time there with only modest corrections, moving in a controlled way within a larger flow. The hollow is not a pit where the object is trapped, nor a flat surface where any push sends it drifting away unchecked. It is a shaped region where the influences around it combine to create a kind of orbital resting place relative to the larger bodies. Across the solar system, similar points exist for other planet and moon combinations. Each pair of massive bodies creates its own set of potential locations, where a smaller object can share their motion with reduced effort. These points and the orbits around them illustrate once more how gravity and motion can combine to produce patterns of relative steadiness. Within a system that is always moving, there are configurations that require fewer corrections, places where a spacecraft can stay aligned with larger partners while the whole ensemble continues its journey around the Sun. On the surface of Earth, gravity's reach is easy to feel as a simple downward pull, but its effects are more varied and subtle than a single direction suggests. One of the clearest examples of this subtlety is the pattern of tides, the slow rising and falling of the oceans under the combined influence of the Moon and the Sun. Twice each day, on average, coastal waters advance and retreat along shorelines, not because the sea itself decides to move, but because the gravitational pulls on different parts of Earth vary in strength and direction. To understand this, it helps to imagine Earth and the Moon together as a system. The Moon orbits around Earth, but they also orbit around a shared center of mass. At any given moment, the side of Earth closest to the Moon feels a slightly stronger pull from lunar gravity than the center does, while the center feels a slightly stronger pull than the far side. These differences are small compared to the overall pull of Earth's own gravity, yet they are enough to stretch the oceans into two broad bulges, one facing the Moon and one on the opposite side. As Earth rotates, different regions pass through these bulges, experiencing high tide when they align with one, and low tide when they pass between them. The Sun contributes its own tidal influence. Although it is far more massive than the Moon, it is also much more distant, so its tidal effect at Earth is comparable in magnitude to the Moon's. When the Sun, Moon, and Earth align, their tidal forces combine to produce larger ranges between high and low tide. When the Sun and Moon are at angles to each other, their effects partially cancel, and the range is smaller. These patterns create the familiar rhythm of spring tides and neap tides over the course of the lunar month. The water does not surge violently under normal conditions. Instead, it rises and falls over hours, following a predictable schedule that coastal communities have observed and used for navigation, fishing, and construction. Tidal forces act not only on water, but also on solid rock and metal. The crust of Earth flexes slightly as it passes through the varying gravitational field, rising and falling by small amounts that can be measured with sensitive instruments. The planet is not perfectly rigid. Under steady stresses, it deforms a little, then returns toward its original shape as the stresses change. Similar effects occur in other systems. Moons orbiting close to their planets can be stretched and squeezed as they travel along elliptical paths, with the strength of the tidal pull changing as their distance varies. This repeated deformation can generate internal heat through friction, warming their interiors and driving geological activity. In some cases, Tidal interactions are strong enough to change orbits and rotations over long time scales. Earth's rotation is gradually slowing because the tidal bulges raised by the Moon are carried slightly ahead of the Earth-Moon line by the planet's spin. The gravitational interaction between the bulges and the Moon transfers angular momentum from Earth to the lunar orbit. As a result, Earth's day lengthens very slowly, and the Moon drifts outward at a rate of a small number of centimeters per year. The effect is too small to notice in a human lifetime, but it accumulates over millions of years, altering the exact rhythm of days and months. Stars and gas giants also feel tides. In close binary systems, where two stars orbit each other at short distances, tidal forces can distort their shapes, pulling them into slightly elongated forms. In extreme cases, material can be drawn from one star to another, forming streams and disks as matter moves along the gravitational gradient. Around massive planets like Jupiter, tidal forces affect their moons and the rings that almost lie in their equatorial planes. The graceful arcs of those rings owe their structure in part to the balance between gravitational pulls, collisions among particles, and the subtle stretching of tides. Underlying all of this is a simple idea. Gravity is not uniform over extended objects. One end of a body feels a slightly different pull than the other end if the gravitational source is nearby. These differences lead to small stretches and compressions, repeated in cycles as objects move along their orbits. The results are often slow, rhythmic changes rather than sudden shifts. Oceans rise and fall, crusts flex, paths adjust, and over long periods systems settle into configurations where tidal effects and rotational motions align in relatively stable ways. In this way, tides show another side of the universe's behavior. Instead of abrupt, chaotic changes, many of its processes are measured and periodic. Forces act, matter responds, and the response follows a pattern that can be described and anticipated. Whether in a coastal inlet, the interior of a tidally heated moon, or the elongated shape of a star in a close binary pair, tidal forces weave a quiet, repeating influence through matter, adding another layer to the overall stability and structure of space. Thoughts do not always become quiet when the surroundings grow still. A room can be silent, the day's work finished, and yet the mind may continue to replay conversations or examine plans. This difference between outer calm and inner motion appears throughout the universe. Large structures can stay stable while activity continues inside them. The solar system keeps its layout while worlds rotate and flex. Galaxies preserve their shapes while stars form and fade within their arms. On Earth, smaller examples are easy to see. A lake on a windless day can look smooth from a distance, mirroring clouds and trees with little distortion. Closer inspection reveals faint ripples from insects touching the surface, slow currents beneath, and continuous motion of water molecules. The lake is not frozen. Its broad outline remains constant, while local changes occur within it. In space, the same idea stretches over greater distances and longer times. A planet, in a stable orbit, follows nearly the same path around its star again and again. From the star's point of view, the planet's average distance and period change only slowly. Inside that planet, continents drift over geological eras, magma circulates, and oceans move in complex currents. Weather patterns form, evolve, and disappear, yet they barely touch the regularity of the orbit. Galaxies offer another example. Seen from far away, a spiral galaxy maintains its overall structure for long periods. Its disk rotates, its spiral arms curve outward, and its central region remains concentrated. Within that framework, gas clouds collapse to make new stars. Supernova explosions enrich surrounding material, and regions of active star formation brighten and fade. Local events are energetic, but their combined effect changes the large-scale shape only gradually. This coexistence is supported by the consistency of physical laws. Gravity behaves the same in quiet regions and in active ones. Electromagnetic interactions follow the same rules in a calm interstellar cloud and in a hot stellar corona. Because these laws do not shift without warning, systems can settle into patterns that endure many small disturbances. Waves may pass through a disk of gas, but it remains a disk. Storms may sweep across a planet's atmosphere, yet the planet keeps its rotation and its orbit. A human body at rest follows the same principle. Its overall structure remains stable while many small processes continue in parallel. Cells exchange substances with their surroundings. Electrical signals move along nerves. Hormones circulate through the bloodstream. Chemical reactions proceed in each organ along well-defined pathways. None of this requires conscious direction. It unfolds within an arrangement shaped over years by growth and adaptation. Within that arrangement, mental activity can vary. Some nights thoughts thin out quickly. On other nights they stay more active, reviewing events or exploring possibilities before slowly losing strength. From the point of view of the body as a whole, these fluctuations are small variations inside a larger pattern that remains secure. Breathing continues. Heartbeat stays within a safe range. The underlying conditions that allow rest do not vanish just because the mind has not yet become quiet. If you notice that thoughts are still moving, that observation can be placed inside this wider context rather than treated as a fault. The universe is full of systems in which motion persists within stable structures. A planet can be secure in its orbit while storms cross its surface. A galaxy can keep its form while new stars ignite and old ones end. In a similar way, a person can be in a state that is ready for sleep, even while some ideas continue to appear and fade. There is no need to force an abrupt stop. Given steady conditions and enough time, activity can settle on its own into quieter forms, guided by the same preference for stable patterns that shapes many structures in the wider cosmos. Between the orbits of the planets, space becomes steadily wider in every sense. Distances increase, densities fall, and the frequency of significant encounters drops. Imagine starting from Earth's path around the Sun and moving outward along a line that passes between the orbits of other planets. At first, you pass through regions where many spacecraft have already traveled, where the influence of the solar wind and the gravitational pull of nearby bodies are well mapped. As you continue, the objects you might meet become fewer and more widely separated. The volume associated with each particle of gas, each grain of dust, and each small body grows larger. Scientists often describe the density of particles in interplanetary space using numbers that seem low compared to air. Near Earth, the solar wind might contain a few particles in each cubic centimeter. This is many orders of magnitude less than the number of molecules in the same volume of air at the surface. As you move farther from the Sun, the density decreases further, yet it does not drop to zero. There are always some ions, electrons, and neutral atoms drifting through the space between planets. Their individual paths are shaped by the combined effects of gravity, electromagnetic fields, and collisions, though collisions become rare as the mean distance between particles grows. Dust particles also inhabit this region. Some are tiny fragments from comets and asteroids, released as these bodies are heated or disrupted. Others are grains that have persisted since early stages of the solar system. They orbit the Sun in their own ways, subject to gravitational pulls and to small additional forces such as radiation pressure and drag from the solar wind. Over time, these influences can cause dust to spiral inward or outward, slowly altering the distribution of material. Seen from a spacecraft, such grains are usually invisible until they strike a detector or scatter sunlight in a particular direction. Their presence is inferred from occasional impacts, from the way they scatter light, and from measurements made by instruments designed to catch and analyze them. A spacecraft traveling through interplanetary space follows a carefully planned trajectory, but its environment changes gradually. Close to a planet, gravity dominates, and the path bends strongly. Farther away, the gravitational influence of that planet weakens, and the craft transitions into a regime where the Sun's pull is the main factor. Engineers describe these regions using concepts like spheres of influence and Hill spheres, which mark the distances at which one body's gravity becomes more important than another's for the motion of a small object. Crossing such boundaries is not marked by any sharp feature in the local environment. Particle densities and field strength shift smoothly, and the spacecraft continues on its way without encountering a physical barrier. Magnetic fields extend through this volume as well. The Sun's magnetic field is carried outward by the solar wind, forming a structure that twists and folds as the Sun rotates and as solar activity changes. Embedded within this field are disturbances that arise from flares and coronal mass ejections, which can travel outward and interact with planetary magnetospheres. For much of the time, however, these variations are modest, and the field provides a relatively stable background that influences the motion of charged particles, while leaving neutral atoms almost unaffected. When scientists describe interplanetary space as quiet, they mean that significant changes are separated by large distances and long times. A probe may travel for hours or days between noticeable events, such as passing through a region of enhanced particle density or encountering the faint tail of a comet. Signals sent from Earth to such a probe take minutes or longer to arrive, depending on the distance, and the return signals require the same travel time in the opposite direction. This finite speed of communication introduces a delay between actions and their consequences that must be considered in navigation and control. From the perspective of the solar system as a whole, interplanetary space acts as the medium through which energy and information move between planets, the Sun, and smaller bodies. Light rays cross it in straight lines except where they are bent by gravity. Particles in the solar wind stream outward, carrying momentum and magnetic structure. Dust and minor bodies follow their orbits, occasionally intersecting and colliding. Despite this activity, the average conditions at a given distance from the Sun can remain similar for long periods. Fluctuations occur around these average values, but the general pattern persists. In this environment, the idea of space as wide, sparse, and quiet captures an important aspect of its character. Wide refers to the enormous distances between major objects. Sparse reflects the low densities of matter, whether in the form of gas, dust, or larger bodies. Quiet points to the low rate of interactions at any given location, especially when compared with the crowded, rapidly changing conditions found within atmospheres or oceans. Motion is present everywhere, but events are spaced out in such a way that each one stands apart, separated from the next by stretches of relative uniformity. Charged particles leaving the Sun form a steady outward flow known as the solar wind. It begins in the Sun's outer atmosphere, a region of very hot, diffuse gas where atoms are stripped of some of their electrons and become ions. At those temperatures, particles move fast enough that some of them can escape the Sun's gravity and stream outward into space. There is no sharp edge where this begins and ends. Instead, conditions gradually change from dense, hot plasma near the Sun to a thin, expanding wind farther away. Near the Sun, the solar wind is dense and fast. As it travels outward, it spreads over an ever larger sphere, so the same number of particles is distributed across a greater area. This causes the density to decrease with distance. By the time the wind reaches the orbit of Earth, its density is low compared to any gas on Earth, yet it is still significant in the context of space. Instruments on spacecraft measure its properties: the number of particles per cubic centimeter, their average speed, their temperature, and the direction and strength of the embedded magnetic field. Although the word wind suggests a strong push, the solar wind at Earth's orbit is more like a continuous, thin stream than a storm. Its pressure on surfaces is small, though not negligible for light objects such as dust grains or very large, thin structures like proposed solar sails. For planets with atmospheres and magnetic fields, the wind becomes more noticeable at higher altitudes, where it interacts with the upper layers of gas and with magnetic field lines. These interactions can produce auroras, alter radiation environments, and affect the tails of comets. The solar wind does not simply carry particles. It transports the Sun's magnetic field outward as well. Because the plasma is electrically conductive, magnetic field lines remain tied to the moving material to a good approximation. As the Sun rotates, it drags these field lines into a spiral pattern, often compared to a rotating sprinkler that sends water outward. This structure, called the Parker spiral, fills much of the inner solar system, influencing how charged particles move and how they are distributed over space. Within this large-scale flow, there are variations. The Sun's activity changes over its roughly 11-year cycle, with more frequent flares and coronal mass ejections during active periods. These events can launch bursts of plasma and magnetic field into the solar wind, forming faster-moving regions that overtake slower wind ahead of them. When such structures pass a planet, they can compress its magnetosphere, increase particle fluxes, and induce currents in conductive materials. From the perspective of interplanetary space, however, these disturbances are localized features traveling through a background flow that remains broadly similar over long times. Comets provide a visible demonstration of the solar wind's influence. A comet approaching the Sun develops two tails. One is a dust tail, formed from particles pushed gently by the pressure of sunlight. The other is an ion tail, created when the solar wind interacts with gas released from the comet's nucleus. Charged particles from the Sun strip electrons from the gas, producing ions that are then guided along magnetic field lines carried by the wind. This ion tail points roughly away from the Sun, following the structure of the wind and field rather than simply trailing behind the comet's path. Planets with strong magnetic fields, such as Earth, Jupiter, and Saturn, carve out their own cavities within the solar wind. The wind is deflected around these magnetospheres, forming bow shocks where the flow slows and heats, and long magnetotails that extend away from the Sun. Inside these regions, charged particles are trapped and guided by magnetic lines, forming belts and zones with different properties. The shapes of magnetospheres change with solar wind conditions, expanding during quieter periods and compressing under stronger flows. Yet the general pattern remains recognizable across many cycles of variation. For bodies without global magnetic fields, like Mars and Venus, the interaction is different. The solar wind can connect more directly with the upper atmosphere, driving processes that strip particles away into space. Over long timescales, this can affect the composition and density of the atmosphere, especially for smaller planets with weaker gravity. Measurements from orbiting spacecraft have shown plumes of escaping ions downstream from such planets, where the wind has carried atmospheric material away. Despite these many interactions, the solar wind maintains an overall character of persistence. It is almost always present, flowing outward in all directions from the Sun. Its speed and density vary, but it rarely stops. Spacecraft traveling outward from the inner solar system move through this environment as through a very thin, continuously streaming medium. Signals sent from those craft come back through the same flow, carried not by the wind itself, but by radio waves that propagate through it. Seen as part of the broader structure of the solar system, the solar wind outlines a vast region dominated by the Sun's influence. It fills the space between planets with a low-density plasma and magnetic field, while beyond a certain distance, its pressure is balanced by the material that belongs to the wider galaxy. The result is a large, approximately bubble-shaped domain whose interior conditions differ from those outside. Within that bubble, the wind provides a gentle, ongoing connection between the Sun and the objects that orbit it, linking them through continuous but moderate interactions rather than through sharp, isolated events. At great distances from the Sun, the solar wind no longer expands freely. It eventually meets material that does not belong to the solar system, the thin gas and plasma that fill the space between stars. The region where the outward pressure of the solar wind is balanced by this surrounding interstellar medium forms the outer boundary of a structure called the heliosphere. The surface where this balance is effectively reached is known as the heliopause. Inside it, conditions are dominated by particles and magnetic fields originating from the Sun. Outside it, the mixture of particles and fields reflects the broader environment of the galaxy. The transition from one regime to the other is not sharp like the surface of a solid object. Instead, it occurs over a range of distances where several related boundaries appear. As the solar wind slows and heats due to its interaction with interstellar material, it passes through a region called the termination shock. Beyond this, in the heliosheath, the flow becomes more turbulent and irregular as it adjusts to the pressure exerted by the material outside. Finally, at the heliopause, the outward pressure of the solar wind is matched by the inward pressure of the interstellar medium, and the character of the particle population changes from solar to galactic. Spacecraft have provided direct evidence of this structure. Probes launched in the late 20th century, after decades of travel through the inner and outer solar system, eventually reached distances where the particle environment shifted in a way that could not be explained by solar influences alone. Instruments recorded decreases in solar wind particles and increases in energetic particles thought to originate in the galaxy. Magnetic field measurements also changed, reflecting a transition from a field carried outward from the Sun to one more closely aligned with the local interstellar field. These observations support the idea that the heliosphere is a bubble embedded in a larger medium, with a boundary that spacecraft can cross. Within the heliosphere, the solar wind and the magnetic field it carries shape the paths of charged particles, including many cosmic rays. Some of these particles are deflected or slowed, so the intensity of certain types of cosmic radiation inside the heliosphere differs from what would be found in interstellar space. This makes the heliosphere a kind of shield, not absolute, but significant, that moderates the flux of high-energy particles reaching the inner solar system. Planets with their own magnetic fields and atmospheres add further layers of protection on smaller scales, but all of them sit inside this larger bubble defined by the Sun's influence. The shape of the heliosphere has been a subject of ongoing study. Early models treated it as roughly spherical, with the Sun at the center and the heliopause at a nearly constant distance in all directions. Later observations and simulations suggest that the interaction between the solar wind and the interstellar medium, combined with the relative motion of the Sun through the galaxy and the structure of the local interstellar magnetic field, may produce a more complex form. Some results indicate a shape that is somewhat squashed on the side facing the incoming interstellar flow and elongated or structured differently on the opposite side. In all cases, however, the key idea remains. There is a region where solar influence dominates and a region beyond where it does not. The size of the heliosphere changes over time. When the Sun's activity is higher, the solar wind can be stronger and the heliopause may be pushed outward. During quieter periods, the pressure of the solar wind decreases, allowing the boundary to contract somewhat. These adjustments are slow compared to human timescales, unfolding over years or decades rather than days. From the perspective of the galaxy, the heliosphere is a small, dynamic bubble moving through a much larger environment, adjusting continuously to the conditions it encounters. Inside this bubble, the planets, moons, asteroids, and comets move along their paths in a medium whose properties are more familiar to scientists than those of interstellar space. The density, temperature, and magnetic structure of the solar wind can be measured and modeled with increasing precision. Space missions can be designed with these conditions in mind, and instruments can be calibrated to distinguish between particles from the Sun and those from outside. The heliosphere, though invisible to the eye, functions as a structured region that gives context to everything that happens within the solar system. Seen as a whole, this arrangement emphasizes the layered nature of space. There is the immediate environment near a planet, shaped by its gravity, atmosphere, and magnetic field. There is the broader environment of the solar wind, filling the heliosphere and linking the planets and smaller bodies to the Sun. Beyond that, there is the interstellar medium, with its own flows, fields, and structures. The heliopause marks the boundary between two of these layers, a frontier where one influence gives way to another, yet both remain governed by the same underlying physical laws. Beyond the outer boundary of the heliosphere, the character of space changes from solar to galactic. The solar wind loses its identity as a distinct outward stream and merges with the gas and plasma that belong to the region between stars. This region is called interstellar space. It is not a separate substance, but a continuation of the same physical reality under different conditions, different densities, temperatures, and field strengths shaped by many stars and past events rather than by a single sun. To get a sense of how sparse this environment is, imagine starting with a cubic centimeter of air at sea level, crowded with molecules that collide all the time. Now remove almost all of those molecules, leaving perhaps a few atoms in a volume the size of a house. Then spread those few atoms out until they occupy a volume the size of a large city. You are still not at the typical densities of many parts of the interstellar medium. In some regions, the number of particles per cubic centimeter is less than 1. Even so, interstellar space is not uniform. There are relatively dense clouds of gas and dust where new stars may eventually form, and there are hotter, thinner regions where past explosions or strong stellar winds have swept material away. Magnetic fields thread through this medium, influencing the motion of charged particles and helping to shape the outlines of clouds and cavities. Shock waves from supernova remnants can compress gas in one region while allowing it to expand in another. Gravity, pressure, radiation, and magnetic forces all contribute to the evolving pattern of densities and temperatures. For an object moving through this environment, the encounter rate with individual particles is very low. A spacecraft that has left the heliosphere would travel for long periods before accumulating many collisions with atoms or dust grains. Light from distant stars and galaxies crosses this medium as well, losing a little energy or being scattered at certain wavelengths. Yet for most purposes it can travel very long distances before its path is noticeably altered. In such conditions, the idea of silence takes on an extended meaning. In a quiet room, silence is the absence of sound. In interstellar space, there is no sound to begin with, because there is no dense medium to carry pressure waves over large distances. There is also a kind of silence in the timing of events. Interactions that would be frequent in air or water are separated here by long stretches in space and in time. A particle may travel for years without meeting another closely enough to exchange energy in a collision. A cloud of gas may take millions of years to respond fully to the gentle pull of gravity, yet the same physical laws that govern busy environments apply without change. Conservation of energy and momentum, the equations of fluid dynamics, and the rules of electromagnetism all remain valid. They simply operate in a regime where changes are slow and sparse. Over long periods, gravity can gather diffuse gas into denser clouds. Radiation can heat some regions and cool others. Magnetic fields can channel flows and resist certain motions. Structures in the interstellar medium shift and merge, but on timescales so long that a single human lifetime samples only a brief moment in their evolution. Interstellar space is therefore not a static void, but a domain where activity is stretched out in both distance and time. The scarcity of matter means that many potential interactions never occur, or occur only after long delays. Motion is present everywhere, but the events that mark it are widely spaced. This extended spacing is a form of quiet, specific to very low-density environments. Not the absence of all processes, but the presence of processes that unfold with great patience. Among the sparse atoms and ions of interstellar space, there moves another population of particles with very different properties. These are cosmic rays, high-energy particles that travel through the galaxy at speeds close to that of light. Most are protons or heavier nuclei. A smaller fraction are electrons or other particles. They do not form a continuous fluid in the same way as the interstellar gas. Instead, they are more like scattered, energetic messengers, each following a path influenced by magnetic fields and past encounters. Many cosmic rays originate in environments where large amounts of energy are released. Shock waves from supernova remnants are prime examples. When a massive star ends its life in a core collapse explosion, it sends a shock wave outward into the surrounding medium. Charged particles crossing this shock can gain energy through repeated interactions, a process sometimes called diffusive shock acceleration. Over time, some of these particles reach energies far beyond those found in ordinary thermal motion and escape into the wider galaxy as cosmic rays. Other sources may include regions near compact objects such as neutron stars and black holes, where strong fields and rapid motions can also accelerate particles. As cosmic rays move through the galaxy, they do not travel in straight lines for long distances. Galactic magnetic fields, though weak in absolute terms, are sufficient to bend their paths significantly. Instead of heading directly outward from their sources, many cosmic rays follow tangled routes, scattering from irregularities in the magnetic field and from inhomogeneities in the interstellar medium. This scattering makes their journey more like a random walk than a direct flight. By the time they reach a particular location, such as the region near the Sun, they have lost much of the directional information that would point back to their point of origin. The flux of cosmic rays at any point in space is usually described in terms of the number of particles passing through a given area in a given time, sorted by energy. At lower energies, the number is relatively high, though still small compared with the number of particles in even a very tenuous gas. At higher energies, the number falls rapidly, but the individual particles carry enough energy that they can produce distinctive effects when they interact with matter. When cosmic rays strike planetary atmospheres, they can create cascades of secondary particles. On Earth, some of these secondary particles reach the surface and even pass through solid objects, leaving traces that can be measured. Inside the heliosphere, the intensity and spectrum of cosmic rays are modified by the solar wind and its magnetic field. As these particles attempt to enter the region dominated by the Sun, they encounter an outward flowing plasma and a complex magnetic structure. Lower energy cosmic rays are more easily deflected, so their numbers are reduced near Earth compared to what they would be in interstellar space. Higher energy particles are less affected and can penetrate more readily. The level of modulation changes over the solar activity cycle. During periods of higher solar activity, the enhanced turbulence and stronger fields in the solar wind can decrease the flux of certain cosmic rays in the inner heliosphere. Planets add further structure to this picture. Earth's magnetic field guides many charged particles away from the equatorial regions and toward the poles, shaping their entry paths into the atmosphere. Some are trapped in radiation belts, circling the planet along magnetic field lines. Others collide with atmospheric atoms and molecules, contributing to ionization and to phenomena such as auroras. Other planets with different magnetic and atmospheric properties interact with cosmic rays in their own ways, producing variations in radiation environments across the solar system. Despite their energetic nature, cosmic rays are rare visitors compared with the more abundant particles of ordinary interstellar gas. In the vast volumes between stars, a cosmic ray may travel for long periods without interacting with anything. Its encounters with magnetic irregularities and occasional collisions are separated by large distances. From the perspective of any small region, the arrival of a cosmic ray is an infrequent event, noticeable only to instruments designed to record it. Most of the time, nothing passes through that region except low-energy particles and photons following their regular courses. In this way, cosmic rays add a layer of sporadic activity to an environment that is otherwise governed by slow, diffuse processes. They are reminders that even in the quietest parts of space, energetic phenomena elsewhere in the galaxy leave their mark. Yet their rarity means they do not dominate the character of interstellar space. They are scattered signals superimposed on a background where the main features are set by gravity, large-scale flows, and the gradual evolution of gas and dust over very long timescales. The distances between stars are so large that ordinary measures lose much of their intuitive meaning. Light, which moves faster than anything else known in nature, requires years to travel from one star to another in our local region of the galaxy. If you imagine light leaving a star and heading toward a neighbor, you have to imagine it continuing at its steady speed for year after year before it reaches its destination. These distances are not empty numbers. They describe how separated events become in space and in time. When something happens near one star, its direct influence on another distant star may be limited to a faint change in radiation that arrives long after the event itself. Most of the time, nothing new reaches that distant point. The background conditions change only slowly, and many processes unfold without direct contact with what is happening elsewhere. You can picture a volume of space that contains a single star and its planetary system, with the next star lying far away. Within that local system, events are frequent. Planets orbit, particles flow, and light reflects and refracts from surfaces and clouds. At the boundary of the system, these activities take the form of outgoing signals that gradually weaken with distance. Beyond a certain point, their influence becomes small compared with the general background of the galaxy. This separation creates a kind of spacing between events. In a dense medium like air, disturbances spread quickly and interact with many neighbors. In the interstellar medium, the same kind of rapid chain reaction does not occur as easily, because there are fewer particles to carry influences and greater distances for them to cross. Changes that are important locally remain local for long periods, while the larger-scale structures respond only to slow accumulations of many small effects. Thinking about this spacing can provide a useful analogy for mental activity. Thoughts, memories, and plans can arrive close together, one triggering another in rapid succession, or they can become more widely separated, with longer intervals between them. The physical conditions that allow thoughts to arise do not need to change for their rhythm to change. Neural processes continue, but the frequency with which one idea leads directly into another can vary. When distances in space are very large, the time between significant interactions grows. A star can move through the galaxy for millions of years without passing close enough to another star to be strongly disturbed. Small perturbations still occur, but they are separated by long stretches in which motion is smooth and predictable. In a similar way, there can be periods when one mental event follows quickly after the next, and periods when ideas appear more slowly, with pauses that lengthen over time. If you picture the mind as a kind of internal space, you can imagine the content of recent experiences as a cluster of nearby stars, each with its own orbit of associated memories and feelings. At first, the cluster may seem dense, with paths crossing often. As you allow attention to expand, it can move outward toward a region where fewer new thoughts appear. The cluster is still there, but its influence becomes less immediate, and there is more room between individual points of focus. This is not something that must be forced. Just as the spacing between stars is a property of the galaxy's structure, the spacing between thoughts can change gradually as the conditions of the moment shift. Reduced sensory input, familiar surroundings, and the absence of urgent tasks all tend to lessen the rate at which new stimuli enter awareness. In those conditions, the mind is free to let some ideas pass without following them, to let others fade without replacement. If sleep has not yet begun, that does not mean that this widening of mental distance is not occurring. The underlying processes that support rest can already be in motion, even while some thoughts continue to appear. With time, their arrival can become less frequent, as if the mental landscape were stretching so that each new idea finds itself farther from the next. In that expanded space, the same physical brain continues its activity, but the pattern becomes sparser and slower, in quiet parallel with the way events are spread out across the wide intervals between stars. From the scale of individual stars and their wide separations, you can extend your view to the shape of a whole galaxy. A spiral galaxy, like the one that contains the Sun, is not just a random swarm of stars. It has a recognizable geometry that persists for very long periods. Seen from far above its disk, the main features stand out. A bright central bulge, a flattened disk filled with stars and gas, and spiral arms that wind outward in broad, sweeping curves. The stars in the disk do not all move at the same speed, yet their combined motion produces a pattern that looks smooth when viewed as a whole. Each star follows its own orbit around the galactic center, guided by the gravity of all the matter in the galaxy, including the invisible contribution from dark matter. The result is a rotating system where the overall structure remains similar from one rotation to the next, even though local details change. The spiral arms are not rigid objects. They are regions where stars and gas are somewhat more concentrated than in the surrounding disk. As material orbits the center, it moves into and out of these denser regions. Gas clouds that pass through an arm can be compressed, triggering new star formation. Young, bright stars then highlight the arm, giving it a clearer outline when the galaxy is observed in visible light. Over time, those stars age and fade, while new ones are born in other parts of the arm or in neighboring regions. The arm pattern persists as a wave of higher density moving through the disk, rather than as a fixed arrangement of individual stars. Beyond the disk, a more diffuse halo extends outward. It contains older stars, globular clusters, and dark matter that provides much of the galaxy's mass. The halo does not have sharp edges. Its density decreases gradually with distance from the center. Within it, satellite galaxies and streams of stars left from past mergers trace out faint structures that can be detected with careful observations. These features show that the galaxy has grown over time by absorbing smaller systems, yet the basic form of a central concentration surrounded by an extended envelope remains. When you consider these components together, the impression is one of organized complexity. Many different motions coexist: rotation around the center, oscillations above and below the disk, local turbulence in gas clouds, and the slow migration of stars as they exchange energy and angular momentum. Despite this, the large-scale shape changes slowly. A spiral galaxy keeps its broad pattern for hundreds of millions of years. The stability arises from the same principles that govern smaller systems. Gravity pulls matter inward, while motion and angular momentum prevent complete collapse. Interactions redistribute energy, smoothing some irregularities and allowing others to persist. Regions that deviate too far from typical orbits are gradually brought back into more common paths, or they are dispersed until they blend into the background. From great distance, the internal variation becomes less visible. The galaxy presents itself as a calm disk with graceful arms, turning slowly around a luminous center. The intricate details of individual stars and clouds merge into a continuous glow. Local storms and flares are still there, but their effects are too small to disturb the overall outline. What remains is a broad, enduring geometry, a large-scale expression of the same physical laws that act on smaller, more familiar scales. Within the calm geometry of a spiral galaxy, each star follows an individual path around the center. The Sun is one of these stars. It moves through the galactic disk on an orbit that takes hundreds of millions of years to complete a single circuit. During that time, the galaxy itself changes only slowly, so the Sun and its planets trace a long, gradual curve through a setting that remains broadly similar from one orbit to the next. The shape of a star's path is influenced by the combined gravity of all the matter in the galaxy. This includes visible components, such as stars, gas, and dust, and invisible components, inferred from their effects, often grouped under the term dark matter. The total mass determines how strongly stars are pulled toward the center and how fast they need to move to maintain their orbits. In the inner regions, stars typically move faster to resist the stronger inward pull. Farther out, where the visible mass thins but dark matter contributes significantly, orbital speeds tend to remain higher than would be expected from visible matter alone. A star's orbit is rarely a perfect circle. Small deviations in speed and direction, interactions with passing clouds, and the influence of spiral arms can stretch the path into a slightly elongated or tilted shape. As a result, a star may move closer to the galactic center at some times and farther away at others, or it may oscillate above and below the central plane of the disk. These variations unfold over long timescales, with each cycle taking many millions of years. From the point of view of a shorter period, such as the age of human civilization, the changes are modest. The Sun's motion is an example. It orbits the galactic center at a distance of many thousands of light-years, completing one full circle in a time far longer than the entire history of human culture. While it moves, the local arrangement of nearby stars shifts slowly. Some neighbors drift away, new ones come within the region that can be called local, and the Sun passes in and out of different parts of a spiral arm. These changes may influence the radiation and gas environment on very long timescales, but they occur gradually enough that the solar system experiences them as gentle trends rather than sudden transitions. Other stars follow their own versions of this motion. Some lie closer to the center, where orbital periods are shorter and the density of stars is higher. Others orbit farther out in the disk or in the halo, where the density is lower and the paths are more extended. In each case, the basic pattern remains: an orbit around a common center, guided by the same gravitational potential. When many such paths are considered together, the result is the smooth rotation of the galaxy as a whole. From a suitably distant vantage point, individual stars blur into a continuous glow, and their separate orbits blend into a single, slow-turning motion. The fine details of each trajectory matter less than the aggregate effect. What stands out is the stability of the pattern. The disk remains intact, the spiral structure persists, the central bulge continues to concentrate light. Local variations still exist, but they are small compared with the overall distribution of mass and motion. This combination of individual movement and collective order is a common feature of large systems. Each component responds to the local forces it feels, yet the statistical result is a structure that changes only slowly. In a galaxy, this structure is the arrangement of stars, gas, dust, and dark matter into a rotating form that endures for billions of years. The orbital dance of stars is not choreographed in the usual sense, but it follows the constraints set by gravity and conservation laws, producing a pattern that is both dynamic and remarkably persistent. When astronomers measure how stars move in galaxies, they find a consistent pattern. The visible matter alone cannot account for the observed motions. If only the stars, gas, and dust we can see were present, many galaxies would not be able to hold themselves together. Stars in their outer regions move too quickly for the gravity of visible matter to keep them bound. Something else must be contributing mass, and therefore gravity, without shining in any straightforward way. The simplest explanation is that there exists an additional component of matter that does not emit, absorb, or reflect light in the ways ordinary matter does. This component is called dark matter. The name does not imply anything mystical. It simply means that, so far, it has been detected through its gravitational effects, rather than through direct light-based observations. Dark matter appears to be spread throughout galaxies and clusters, forming an extended halo around the visible parts. In a spiral galaxy, dark matter acts like a quiet scaffold. It deepens the gravitational potential well in which stars and gas move. When a star orbits the galactic center, it responds to the total mass enclosed within its orbit. That total includes both luminous matter and dark matter. The extra mass allows stars farther from the center to move faster than they would if only visible matter were present, without being flung into intergalactic space. The result is a rotation curve that remains relatively flat over a wide range of radii, instead of decreasing sharply at larger distances. This influence is not confined to individual galaxies. In clusters of galaxies, dark matter provides additional binding mass that holds the cluster together. Without it, the observed motions of cluster members would be too energetic for the cluster to remain intact over long timescales. Gravitational lensing measurements, which track how light from more distant sources is bent by the gravity of foreground structures, also point to large amounts of unseen mass. These lensing effects reveal maps of total mass that include both visible matter and the dark component that surrounds it. Despite its importance, the detailed nature of dark matter remains an open question. Many experiments search for possible particle candidates, looking for rare interactions between dark matter and ordinary matter in sensitive detectors. So far, results have constrained possibilities without providing a clear identification. Observations on cosmological scales, including the distribution of galaxies and the temperature variations in the cosmic microwave background, support models in which dark matter is relatively cold and moves slowly compared to light. Such matter would have clumped early in the history of the universe, providing seeds around which ordinary matter could gather. From the perspective of galactic structure, what matters most is that dark matter behaves in a stable, predictable way under gravity. It does not radiate away energy in the manner of gas, so it does not collapse into thin disks or tight clumps as easily. Instead, it forms broad halos whose shapes change only gradually. Visible matter then settles within these halos, forming stars and disks that trace out the gravitational landscape set by both components. Over billions of years, this arrangement leads to systems where the unseen mass guides the motion of the scene, without needing to call attention to itself through light. If you imagine a galaxy as a glowing pattern suspended in space, you can think of dark matter as the invisible framework that supports that pattern. It does not dictate every detail, but it sets the overall depth of the gravitational well and the shape of the potential in which stars move. The quiet persistence of this underlying mass allows galaxies to rotate, cluster, and merge within a structure that remains coherent over long periods, governed by the same gravitational law that operates in more familiar environments. On scales larger than a single galaxy, a different pattern appears. Galaxies are not scattered randomly through space. They gather in groups and clusters, and these clusters connect along extended structures called filaments. Between the filaments lie broad regions with far fewer galaxies, known as cosmic voids. The result is a three-dimensional network often described as the cosmic web. You can picture this web by imagining a very large sponge or a piece of lace, where the solid parts trace out lines and knots, and the holes represent emptier regions. In the universe, the threads of this structure are made of galaxies and the matter that surrounds them, while the holes are the voids. Observations from large sky surveys, which map the positions of hundreds of thousands of galaxies, reveal this pattern when their locations are plotted in 3 dimensions. Dense knots mark the positions of galaxy clusters. Long, thin chains connect these knots. Large, nearly empty volumes open between them. The origin of this structure lies in the early universe. Tiny fluctuations in density, present when the universe was very young, were amplified over time by gravity. Regions that started out slightly denser attracted more matter, growing into the filaments and clusters seen today. Regions that started out slightly less dense lost matter to their surroundings and became voids. Dark matter plays a central role in this process, providing most of the mass that responds to these small initial differences. Ordinary matter falls into the gravitational wells created by dark matter, forming the galaxies and gas clouds that we can observe. Computer simulations that start from initial conditions, consistent with measurements of the cosmic microwave background, reproduce this web-like pattern. They show how matter flows along filaments toward cluster centers, how smaller structures merge into larger ones, and how voids expand as matter drains away from them. The details of any specific filament or cluster depend on the exact arrangement of early fluctuations, but the overall statistical pattern matches what is seen in real galaxy surveys. This agreement supports the idea that the cosmic web is a natural outcome of simple physical laws acting over very long times. Within filaments and clusters, galaxies move under the combined gravitational pull of all the matter in the region. Their orbits can be complex, influenced by close encounters and by the deep potential wells of massive clusters. Gas within these environments is heated, shocked, and sometimes stripped from galaxies as they fall into denser regions. Star formation rates can be affected by these processes, leading to differences between galaxies in clusters and those in more isolated settings. Even so, the large-scale arrangement of filaments and nodes persists, changing only gradually as matter continues to flow along preferred directions. Cosmic voids, though less populated, are also important. They occupy a large fraction of the universe's volume. Within them, galaxies are sparse, and gravitational fields are weaker. Matter that does exist there expands with the overall cosmic expansion with fewer local disturbances. The contrast between dense filaments and wide voids highlights how gravity can amplify small differences into pronounced structures given enough time and enough space. Seen from a very distant and abstract perspective, the cosmic web is another expression of balance between attraction and expansion. Gravity pulls matter together into clusters and filaments. The overall expansion of the universe tends to stretch space, increasing distances. The present-day distribution of galaxies reflects the outcome of these opposing tendencies acting on the initial pattern of fluctuations. The result is a network that spans billions of light-years, intricate in detail yet broadly regular in its statistics, showing that even on the largest scales the universe organizes itself into recognizable forms rather than remaining featureless. Cosmic voids are the large, relatively empty regions that open between the filaments and clusters of the cosmic web. They are not perfect vacuums, but compared to the denser parts of the universe they contain very little. A typical void may span tens to hundreds of millions of light-years, while hosting far fewer galaxies than regions of similar size in a filament. The matter that is present is spread thinly, forming a low-density background through which a small number of galaxies and gas clouds move. These voids form naturally as gravity amplifies small initial differences in density. Regions that begin slightly underdense lose matter to their surroundings as material flows toward nearby overdense areas. Over time, the underdense regions become emptier, while matter accumulates along the filaments and in clusters. The process is gradual, driven by many small motions of particles and galaxies rather than by sudden events. As the universe expands, voids also expand, and their interiors become even more sparsely populated. Galaxies that do lie within voids often show different properties from those in crowded environments. With fewer close neighbors and weaker tidal forces, their interactions are rarer. They may retain more of their gas for longer periods, affecting how and when they form stars. Observations and simulations suggest that void galaxies tend to be relatively isolated, with long travel times to the nearest large groups or clusters. Their surroundings are quiet in the sense that major gravitational encounters are infrequent. The gravitational field inside a void is smoother than in denser regions. There are fewer massive structures to create strong local gradients. As a result, galaxies in voids experience gentle, large-scale flows rather than complex motions around nearby clusters. Matter gradually drifts outward from the centers of voids toward their edges, where it joins the surrounding filaments. This slow rearrangement continues as the universe expands, but the contrast between the emptiness of voids and the richness of filaments persists. From a statistical point of view, voids occupy much of the universe's volume, even though most of the matter resides in the denser structures around them. If you were to choose a point in space at random, it would more likely fall inside a void than inside a cluster. Yet because matter and light are concentrated in filaments and galaxies, our observations naturally focus on the brighter, denser parts. Mapping surveys that chart galaxy positions in 3 dimensions reveal the voids indirectly, as the empty space is left when the visible structures are connected. In this way, cosmic voids highlight an extreme form of sparsity. They show how gravity and expansion together can create regions where very little happens on short timescales. While filaments and clusters host frequent interactions, mergers, and bursts of star formation, voids evolve more slowly. Their few galaxies move along long, smooth trajectories, and the low-density gas inside them changes condition over extended periods. The universe thus contains not only crowded, active zones, but also vast, nearly empty domains, where the main feature is the absence of strong disturbances. From the perspective of the cosmic web, every galaxy, star, and planet occupies a place within a larger arrangement. The filaments carry clusters of galaxies where matter has collected under gravity's pull, while voids stretch between them as broad, underdense spaces. Within one of these filaments lies the galaxy that contains the Sun. Within that galaxy, far from the center, the Sun follows its orbit through the disk. Around the Sun, the planets trace their paths, and on one of those planets, continents, oceans, and atmospheres shape conditions at the surface. It is possible to follow this chain step by step. A galaxy sits at the junction of filaments in a cluster. The cluster is part of a still broader structure that extends across hundreds of millions of light years. The Sun is one star among many in its galactic neighborhood, itself surrounded by a cloud of smaller bodies and by the larger planets. Each level has its own patterns: galaxy clusters with their motions and mergers, galaxies with their rotations and star formation, planetary systems with their orbits and smaller cycles. None of these layers exists in isolation. Each is influenced by the one above and below, but the influences are often gentle and gradual. The position of the solar system in its galaxy does not change quickly. The broad track along which the Sun moves is determined by the overall gravitational field, which includes both visible matter and dark matter. Over long times, the environment may shift as the galaxy evolves, passing spiral arms, encounters with gas clouds, and the slow rearrangement of nearby stars. On shorter timescales, the local conditions experienced by the solar system are remarkably stable. The same basic pattern of day and night, seasons, and planetary motions holds across many generations. On Earth, the environment is further organized by the planet's own properties. Its rotation gives rise to the apparent daily motion of the sky. Its axial tilt and orbit around the Sun set the rhythm of seasons. Its internal heat and plate tectonics gradually reshape continents and ocean basins. Above the surface, the atmosphere and oceans circulate, redistributing heat and moisture. These processes operate on a range of timescales, from hours for weather systems to millions of years for geological change. Together, they define the conditions in which ecosystems develop and human activities take place. Importantly, none of these patterns depends on constant intervention. The orbits of planets, the rotation of galaxies, and the expansion of the universe proceed according to physical laws that do not require supervision. When initial conditions are set, the equations of motion determine how systems evolve. Random influences and small disturbances can shift details, but the overall structures emerge from the interaction of gravity, pressure, rotation, and other fundamental effects. This layered stability means that many aspects of the environment are reliable. The sun will rise again because Earth's rotation continues. Seasons will follow one another because the orbit and tilt remain within narrow limits. The galaxy will go on turning because the mass distribution and gravitational field change only slowly. On larger scales, the cosmic web will continue to guide the flow of matter along filaments and away from voids. Within this framework, individual events are small variations. A storm, a fluctuation in solar activity, or a change in local conditions is significant on its own scale but minor compared with the patterns that extend above and below it. The arrangement of structures from cosmic web to planetary surface provides a context in which such variations occur. By recognizing that context, it becomes easier to see that many features of the world are not fragile or arbitrary, but are supported by deeper regularities that span great distances and long periods of time. In addition to galaxies, stars, and gas, the universe is filled with a faint, almost uniform glow known as the cosmic microwave background. This radiation is the remnant of an earlier, hotter phase of the cosmos. When the universe was young and dense, matter and light were closely coupled. Photons scattered frequently from charged particles, and the medium behaved like an opaque plasma. As the universe expanded and cooled, conditions changed. Electrons combined with nuclei to form neutral atoms, and photons were no longer blocked at every step. They began to travel freely through space, carrying with them a record of the conditions at the time of their release. Today, those photons are observed as microwaves, with wavelengths much longer than visible light. Their temperature corresponds to a value only a few degrees above absolute zero. Despite this low energy, the cosmic microwave background is present in every direction. Sensitive instruments on satellites and ground-based observatories detect it as a nearly uniform glow across the sky. Small variations in its temperature and polarization, at the level of tiny fractions of a percent, encode information about the early distribution of matter and the seeds of later structure. The smoothness of this background is striking. Over large angular scales, the temperature is almost the same wherever you look. This uniformity tells us that the early universe was remarkably even in its density and temperature, with only slight fluctuations. Those fluctuations were enough for gravity to amplify over billions of years, leading to the formation of galaxies, clusters, filaments, and voids. Without them, matter would have remained spread out too evenly for large structures to develop. With them, but kept small, the universe could evolve into its present form without collapsing everywhere at once. Measurements of the cosmic microwave background have become one of the main tools for understanding cosmological parameters. By analyzing the pattern of temperature variations across the sky, scientists can infer the relative amounts of ordinary matter, and dark energy, as well as details about the universe's overall geometry and its expansion history. The background thus serves as a kind of reference surface, a relic signal that ties current observations to conditions billions of years in the past. For everyday experience, the cosmic microwave background is imperceptible. Its photons pass through the atmosphere and through your body without noticeable effect, adding a tiny contribution to the thermal environment that is far outweighed by local sources of heat. It is a background in both a technical and an intuitive sense, always present, rarely noticed, and stable over human timescales. Its intensity and spectrum have changed only gradually since it was first released, modulated mainly by the expansion of space that stretches its wavelengths and lowers its apparent temperature. In the larger picture, this radiation field is another quiet layer of the universe. It fills space with a low level of energy that is nearly the same everywhere, against which other variations stand out. Galaxies, stars, and planets are built on top of this uniform glow. Their light and motion add local structure to a backdrop that remains simple and predictable. The cosmic microwave background does not drive daily events, but it anchors cosmology, providing a steady reference that confirms the overall coherence of the universe from its early stages to the present. Over time, the cosmic microwave background does not remain exactly the same. As the universe expands, the distances between points in space increase, and the wavelengths of the background photons stretch with that expansion. Longer wavelengths mean lower energy. What began as a glow in the visible or infrared ranges in the early universe has gradually shifted into the microwave band and will continue to slide toward even longer wavelengths in the far future. The temperature associated with this radiation has been decreasing throughout cosmic history, moving from values compatible with glowing plasma down to a few degrees above absolute zero today. This process can be understood without imagining space as a substance that cools in the usual sense. Instead, the key idea is that when distances grow, the oscillations that describe light become more spread out. A photon is characterized by its wavelength and frequency. As space expands, the wavelength stretches and the frequency decreases. So each photon carries less energy. The total number of photons remains roughly the same, but their individual energies drop. The result is a radiation field whose overall temperature declines in step with the scale of the universe. In many physical systems, there is a tendency for energy to become more evenly distributed over time. Hot regions transfer energy to cooler ones until temperatures approach a common value. This approach to thermal equilibrium is familiar in everyday situations. A hot drink left on a table cools as it shares heat with the surrounding air. A metal rod heated at one end slowly reaches a more uniform temperature along its length. On cosmic scales, the early universe underwent a similar process, with matter and radiation interacting frequently until their temperatures matched. Once photons decoupled from matter and began to travel freely, their further cooling was driven mainly by expansion rather than by direct exchange with matter. Today, the cosmic microwave background serves as a reference temperature for the universe as a whole, even though many local environments depart from it. Stars, planets, and warm clouds of gas are much hotter. Dark, empty regions far from sources of radiation may be closer to this background level. Over very long time scales, as stars exhaust their fuel and energy sources become rarer, more parts of the universe will drift toward temperatures set by diffuse radiation and by particles moving near rest. The general direction is toward a more uniform, lower energy state, even if many pockets of higher activity remain for extended periods. If you think of this slow cooling as a gradual release of stored energy, the universe can be pictured as moving from an early, tightly packed state to a late, more diffuse one. There is no sudden boundary where this change begins or ends. Instead, each stage follows from the previous one through the same physical laws, with expansion stretching wavelengths and gravitational clustering shaping where matter collects. The background radiation records this shift, its spectrum and temperature bearing silent witness to the passage from dense plasma to transparent space filled with galaxies and clusters. In a simpler analogy, it resembles the way a system, once heated and then left alone, tends to settle. High contrasts in temperature fade, sharp gradients soften, and differences smooth out. Locally, fluctuations can still occur, but the overall trend is toward a quieter distribution of energy. On the largest scales, the cosmic microwave background embodies this trend, its temperature sliding slowly downward as the universe grows, marking a long, gentle progression that continues regardless of shorter, local events. The universe contains many events that, taken in isolation, look sudden and intense. Stars explode as supernovae, releasing large amounts of energy in a short time. Galaxies collide and merge, sending gas clouds into new orbits and triggering waves of star formation. Black holes accrete matter and produce jets that pierce surrounding gas. Each of these processes can drastically reshape its immediate environment. Yet when viewed against the full background of cosmic structure, they appear as local disturbances superimposed on a framework that remains stable. The key to this stability is that the underlying physical laws do not change. Gravity continues to act according to the same equations before, during, and after a dramatic event. Conservation of energy and momentum still applies. Electromagnetic interactions follow the same rules in a quiet interstellar cloud and in the hot shock front of a supernova remnant. Because these laws are fixed, the outcomes of local upheavals are constrained. Material thrown outward in an explosion follows specific trajectories. Shock waves slow as they sweep up surrounding gas. Heated regions cool by radiation and expansion. Over time, even strong disturbances blend into the larger pattern. Consider a supernova in a spiral arm. For a short interval, it outshines its host galaxy in certain wavelengths. It drives a shock into the surrounding medium, compressing gas and potentially triggering the formation of new stars. On scales of a few light years, the event is transformative. On scales of thousands of light years, the arm remains in place, its overall mass and rotation only slightly altered. The galaxy as a whole notices the supernova only as a small adjustment in the distribution of energy and heavy elements. Its spiral structure, rotation curve, and dark matter halo remain essentially unchanged. Galaxy mergers follow a similar pattern. When two galaxies approach, their stars mostly pass by one another without direct collision, because the space between stars is large. Gravitational forces reshape orbits, stretching tidal tails of stars and gas. Over hundreds of millions of years, the two systems can settle into a single, new galaxy with a different morphology. While this is a major reorganization locally, it still obeys the same conservation principles. The total mass, energy, and momentum are redistributed, but not lost. The merged galaxy then continues its own orbit within the larger structure of a cluster or filament, fitting into the cosmic web in a way that looks smooth from a sufficient distance. On smaller scales, planets experience impacts, atmospheric changes, and internal rearrangements. A large collision can alter a planet's surface or tilt its axis. Volcanic activity can reshape landscapes. Over geological times, continents move and climates shift, yet the planet remains bound to its star, and its orbit changes only slightly unless extreme events occur. The main parameters that define its path and its place in the stellar system are robust against most local changes. This pattern, in which local events are sharp and global trends are gradual, is common across many levels of structure. Disturbances redistribute matter and energy, but they do so within boundaries set by larger-scale conditions. The deeper gravitational wells of galaxies and clusters, the overall expansion of the universe, and the constraints imposed by conservation laws ensure that, while details can vary widely, the broad arrangement of matter and motion remains coherent over long periods. Human experience is tied to short intervals. Minutes and hours structure days. Days and weeks define routines. Years mark larger cycles such as seasons, education, careers, and generations. Within these scales, events feel urgent. A decision delayed by a day can seem significant. A deadline measured in weeks can dominate attention. The mind adapts to this rhythm, treating near-term changes as especially important. Cosmic processes unfold on very different schedules. The orbit of the Sun around the center of the galaxy takes hundreds of millions of years. The full evolution of a typical star, from its formation in a collapsing cloud to its final stages as a white dwarf, neutron star, or black hole, spans millions to billions of years. The growth of structure in the cosmic web, from small fluctuations in the early universe to the complex network of filaments and voids observed today, covers most of the universe's history. These timescales are so long that even major steps in those processes appear almost fixed when viewed over human lifetimes. When astronomers say that a galaxy is stable, they do not mean that nothing changes within it. They mean that its overall properties, such as mass distribution and rotation pattern, change only slightly over many millions of years. Star formation continues, supernovae occur, and gas flows along spiral arms, but the large-scale form persists. For a human observer, the galaxy's outline would look essentially the same from birth to old age. Any differences would be too subtle to detect without careful measurement and archival comparisons. The same applies to planetary orbits and many geological processes. The parameters that define Earth's orbit change, but slowly. Small variations in eccentricity, tilt, and precession accumulate over tens of thousands to hundreds of thousands of years. These changes influence climate patterns, but they are gradual compared with the pace of daily weather or seasonal cycles. Plate tectonics rearranges continents and ocean basins over tens of millions of years. Mountain ranges rise and erode over similar intervals. At any given moment, such movements are imperceptible without instruments, even though they reshape the planet over long periods. This disparity between human and cosmic timescales has practical consequences. It allows scientific models to treat many parameters as constant when studying short-term behavior. Earth's rotation rate, the Sun's output, and the galaxy's gravitational potential can be taken as fixed for the purposes of understanding phenomena that last years or centuries. Their slow evolution becomes important only when looking at much longer histories, such as the development of climate over geological epochs or the chemical enrichment of the galaxy over successive generations of stars. It also provides perspective. Events that feel large and immediate in personal experience occur within a framework that is largely unaffected by them. The orbit of Earth, the structure of the solar system, and the configuration of the local galaxy continue along their paths with very little sensitivity to short-term variations near the planetary surface. This does not diminish the importance of local events on their own scale, but it places them within a wider context where the background is steady. When considering the universe as a whole, urgency is a relative concept. Some processes are rapid compared to others, but many that shape the large-scale structure operate on times so long that almost any human interval becomes brief by comparison. Recognizing this difference helps clarify which changes are transient and which are part of longer trends. The separation between them allows local systems to fluctuate without constantly disrupting the broader patterns that extend across vast distances and deep stretches of time. Stillness in nature rarely means that nothing is happening. More often, it means that motion has settled into patterns that no longer require large adjustments. An object in a stable orbit continues to move, but it does so in a way that repeats with little variation. A rotating planet turns at a nearly constant rate. A galaxy disk revolves while maintaining its general shape. The apparent calm comes from alignment with conditions that allow motion to proceed smoothly, rather than from the absence of motion itself. In orbits, this alignment appears as a match between speed, direction, and gravitational pull. If a planet moves too slowly for its distance from a star, it spirals inward. If it moves too quickly, it can drift outward or escape. When its speed and distance fall within a certain range, it follows a closed path that repeats. The same is true for moons, ring particles, and stars in galaxies. Each object finds a trajectory that fits the gravitational landscape it inhabits. Once established, that trajectory can persist for long periods, with only small corrections from encounters or gradual changes in the surrounding mass distribution. Other natural systems show comparable behavior. In an atmosphere, large-scale circulation patterns arise from the balance of heating, rotation, and the shape of the planet. Jet streams and trade winds are not static, yet they maintain preferred paths because they reflect stable relationships among temperature gradients, pressure fields, and the Coriolis effect. In oceans, major currents follow routes set by winds, continental outlines, and density differences. These flows vary, but their main outlines are recognizable over many years. Within living organisms, regular rhythms emerge from feedback between many components. Heartbeats, breathing cycles, and patterns of hormonal release are examples. Each involves motion and change, yet each can settle into a range where inputs and outputs match over time. The system does not freeze, it continues to adjust to internal and external conditions. Still, within certain bounds it behaves predictably, returning to similar values after deviations. In all these cases, stillness is better described as a state in which opposing tendencies are balanced and variations are contained. Gravity and motion, heating and cooling, excitation and inhibition, all act together. When their combined effect remains within a stable range, the system avoids drastic swings. It can absorb disturbances and then return toward its characteristic patterns. Thinking about stillness in this way shifts the focus from stopping motion to cooperating with the conditions that lead to regular behavior. A planet does not cancel gravity to keep its orbit. It moves in a way that works with gravity. A current does not eliminate differences in temperature and salinity. It flows along paths that arise from them. In similar fashion, many forms of rest do not depend on removing every fluctuation. They depend on allowing processes to proceed within ranges where they support, rather than disrupt the system as a whole. Segment 30. Across all the scales traced so far, from the edge of Earth's atmosphere to the gaps between stars and the filaments of the cosmic web, a consistent picture appears. Space is not empty in any absolute sense, but its contents are often sparse and widely spaced. Sound fades where there is no dense medium to carry it, yet light and other electromagnetic waves cross the void, linking distant regions. Gravity acts everywhere, quietly organizing matter into orbits, disks, galaxies, and clusters. Dark matter adds an unseen framework that deepens gravitational wells and stabilizes large structures. Interplanetary space is filled with a thin solar wind and threaded by magnetic fields. The heliosphere forms a bubble in which the sun's influence dominates, set within the wider interstellar medium. Beyond it, gas, dust, and cosmic rays move under the combined effects of galactic gravity and magnetic fields. On still larger scales, galaxies gather into the filaments and clusters of the cosmic web, leaving wide voids between them. These structures arose from small fluctuations in the early universe, amplified over time while the cosmic microwave background cooled and its photons stretched to longer wavelengths. Throughout this landscape, stillness is relative. A spacecraft in orbit moves quickly but experiences weightless calm. Planets follow persistent tracks around their stars. Stars orbit galactic centers on paths that change only slowly over spans far longer than human history. Galaxies rotate and drift within clusters while preserving their overall forms. Local events can be energetic, from supernovae to galaxy mergers, but they unfold within a framework of physical laws that remain stable. The large-scale structure adjusts gradually, even as smaller regions undergo rapid change. The same principles carry down to familiar environments. The bed that holds a resting body balances gravity with supporting forces. The air around it transmits small sounds through countless molecular collisions. Inside the body, many processes continue automatically within ranges shaped by long adaptation. These local conditions sit inside larger patterns: the planet's orbit, the galaxy's rotation, and the expansion of the universe. None of these broader motions depends on momentary concerns. They proceed according to rules that have held for billions of years. Knowing this, you can regard the quiet around you as part of a much wider quiet that does not mean the absence of motion, but the presence of order. The universe is active at every scale, yet its activity follows patterns that give rise to long-term stability. Orbits persist, structures endure, and background signals like the cosmic microwave glow remain almost unchanged over human lifetimes. That stability provides a context in which temporary fluctuations can subside without threatening the whole. Whether you are already drifting off or simply lying still with your eyes closed, you remain embedded in that ordered universe, on a planet held by gravity, in a solar system enclosed by the heliosphere, in a galaxy supported by a dark matter halo, all within the quiet web of cosmic structure. The same laws that guide distant stars also govern the small region of space you occupy now. With that thought, this journey through space and stillness comes to an end. We from Sleepy Stories wish you a good night.